Okay, so we'll go ahead and get started. You took your exam 1 on the weather day, so now we're moving into module 2, which is on oxidation state 1 functional groups. So these are alcohols, thiols, ethers, thioethers, and we'll talk about amine chemistry as well. So again, oxidation state 1 means that the carbon is only bonded to one heteroatom through a sigma bond. Any questions before we get underway? So we'll talk a little bit about alcohols, physical properties, nomenclature, and then we'll spend quite a bit of the lecture on how alcohols are made from carbonyl compounds. So overall, that's a reduction. Alcohols have the hydroxyl group, so OH, and they're named according to finding the longest carbon count chain in the alkane, and then you take out the E and add OL as the parent functional group. So here's the chain. That's the carbon count. The class of alcohol is you're looking at the carbon that's bearing the OH group. So for example, this is methanol. Oop. If we go up 1 to ethanol, so if you were sad that USM lost a football game, you might have drank some ethanol over the weekend. So ethanol is the alcohol in any adult beverage, whether it's wine, whiskey, beer, whatever. So ethanol is a primary alcohol, and the carbon bearing the OH group is called the carbonyl carbon. So you're really looking at that to see how many carbons are attached to that to classify it. So ethanol has 1, and as we'll see, if you start branching off from that, you get secondary and tertiary alcohols. So as you see, we've just dropped the E and hired the OL. There's the molecular weights. The melting point and boiling points are given. We'll talk about a trend that they have, going from alcohols that are sort of at the end of the chain, like primary type alcohols, how the boiling point will differ when it becomes secondary or tertiary. As you start crowding the OH group, the boiling point changes according to a trend. Notice for 3 carbon count, you can have primary and secondary. And there you have to specify the location of the hydroxyl group, and that's this number here. That number in the name is independent of the classification. So this would be 1 propanol. And the 1 is just telling you the location of the OH group. A constitutional isomer would be 2 propanol. And then when we get into 4 carbons, you can see that we have 1, 2, and 3 classes. So primary, secondary, and tertiary. So a tertiary alcohol is the 2-methyl 2-propanol. So this is commonly called TERT, T-E-R-T, TERT butanol, or the IUPAC name 2-methyl 2-propanol. And so the carbonyl carbon or carbonyl carbon, I've highlighted in blue. You can see that has 3 carbons attached to it, so that's tertiary. So just a little bit of review of nomenclature. I would expect your final exam probably has 2, maybe 3 max nomenclature problems. And you know, just to recap, you're always finding the longest chain. And then after that, you know, you're going to get the longest chain, that's some alkane name. Then you have to find the highest oxidized functional group. And so remember, an oxidation state of carbon, you're just counting the bonds to a heteroatom. So we can see that this carbon right here in blue, that's the one bearing the OH group. There's just a single bond, so it's at an oxidation state of 1. As we learn more about these functional groups, if we go up higher, 2 and 3, then the names can get a little bit more complicated because you have to decide what gets the parent functional group. But it's mainly based on oxidation state. So we'll say that's oxidation state 1. It's OH, so it's got to be named as an alcohol. So if we find the longest carbon chain, so that's 1, 2, 3, 4, 5, 6. So it's going to be a hexane derivative. So that will become hexanol. And we have to specify where the OH is located and what other substituents there are. So you can name, or you can number the chain 2 ways, one of which will be correct. So the correct way is numbering it that way. We'll finish naming it and I'll show you the incorrect way and why it's incorrect. So it's going to be now 3-hexanol. And now we need to put all this stuff in front of it. And we can see at position 4, there's a single carbon, so that's 1 carbon is methane. It's a substituent, so it becomes methyl. So this would ultimately be 4-methyl 3-hexanol. And that would be choice A. The number, that 3, is sort of the newer rules where the 3 directly precedes that functional group. You can stick it in front of the total chain. That's what I'm used to doing. So I put it right here, but you can put it, you know, after the N and before the O is fine. So the sum of the substituent numbers, 4 and 3, equals 7. In the rules for nomenclature, that sum has to be the lowest possible number it can be. So if you were to number the chain the other way, you would get 3-methyl 4-hexanol. You say, Donahue, you're a liar. It's the same sum. 4 plus 3 equals 7. But the issue is the OL group, that's the priority group, so it must get the lowest number possible. So if you did run into that scenario where they're the same, the parent has to get the lowest possible number it can. So here's a question where you're given those alcohols up through carbons 1, 2, 3, 4. Oh, sorry, that's 3, 4, 4, and 4. And the classes were primary, 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 secondary, primary, secondary, tertiary. And what this is asking you is looking at the boiling point, we sort of draw these lines. So see, for carbon count 3, you go primary to secondary, the boiling point decreases. And then carbon count 4, primary, secondary, tertiary, it's decreasing in a trend. So the way that I like to rationalize this is these primary ones look like spaghetti. So when you boil your water, you put your noodles in, eventually they become all entangled, right? And so the OH group at the end of the chain is better able to hydrogen bond, so the molecules entangle more. When they're secondary or tertiary, the molecule starts looking more spherical. So rather than a strand, it looks more like an M&M candy. And so the contact between M&Ms is pretty small, right? So boiling, if you're taking something from liquid to gas, you have to add heat. So the entanglement, that's more interactions. You have to add more heat to get that entanglement overcome. Whereas with these M&M ones, the contact isn't great, so you don't have to add as much heat, and therefore the boiling point decreases as the class of the alcohol goes up. So I think just qualitatively B would be the best answer here. Again, molecular weight really doesn't influence physical properties too much. It's more of the functional groups present in the molecule. So how do we know that there's an alcohol or OH group in the molecule? We learned last semester about infrared spectroscopy. And this slide is just a summary with the green light telling you that that technique gives you the most confidence in the data. Yellow is sort of ambiguous in a sense, and if it's red, then it's not going to tell you if it's there or not. So as we'll see in the next slide, the OH typically has that really broad stretch in the IR, and it's broad because of hydrogen bonding. So remember that the oxygen has 2 lone pairs. And so with this dashed line, that's a hydrogen bond. And so the signal becomes really broad because I've just shown you 2 molecules of an alcohol, but you can imagine if you have a mole of something, they're all surrounding each other. And even though it's an O to H hydrogen bond, there's still a lot of them. And so they can exist in different stretching modes. Not so much for this class, but if you go on to take another chemistry class called structural elucidation, you'll learn about mass spec fragmentation patterns. If an alcohol is in there, it'll typically be lost as water from the parent ion. So again, in terms of just reviewing stuff for your final, M is typically called the parent ion. Proton NMR, even though the alcohol has an H group, and you're like, okay, I should see that, because of the hydrogen bonding and other things that happen, that signal tends to get washed out, so you won't necessarily see it all the time. So that's why that's yellow. And then for carbon, because you're detecting carbon and not oxygen or H, you can still sort of infer things because you'll have a shift that's further away from 0. Again, once you get above, 30, you can say with confidence, I have a heteroatom attached to this carbon. And so here is an IR spectrum of 1-butanol. And so my organic 1 class this morning, they're going to take one of their spectroscopy exams on Wednesday. And what I told them, and I'll tell you, is like the way this spectrum looks, all I did was take a picture of over in the tutorial center. There's just books of these IRs. But there's also a website called SDBS. It's a Japanese site. Japanese, if I can spell that right. You just type in the molecule name, it'll give you the data. And so on your exams, when you see IRs and stuff like that, it's either from SDBS, those books in the tutorial center, or the US government has the NIST web book. That's where I get these from. So if you need a review, you can just go look up the main functional groups to see what this data looks like. So in region 1 of the IR, this really broad signal here is due to your OH, so the oxygen-hydrogen stretching. And when I say broad, I mean sort of the start and then stop. That span of wave numbers, because it's so big, it's broad. There's a lot of different stretching modes within that just OH stretch. But that's the telltale sign that, okay, I have OH somewhere. So we know that oxygen always has 2 sigma bonds and then 2 lone pairs. So in the functional group of the alcohol, the carbon-oxygen bond is polarized. So this is due to electronegativity. The oxygen lone pairs make it delta minus, so the carbon has to be delta plus. And being able to do that, we're just using the periodic table here. Where electronegativity increases towards fluorine across the period and then up the group. So when an alcohol hydrogen bonds, I'll just use that 2-propanol as the example. So it's a hydrogen bond donor and an acceptor. A donor is giving the OH bond, then as an acceptor, the lone pair is what is accepting it. And again, from the lone pair to that H, that dashed line is the hydrogen bond. So keep in mind that OH is a polar covalent bond. The oxygen and hydrogen are sharing those. Oxygen gets it a little bit more because it's more electronegative. So a hydrogen, when we say hydrogen bond, it's not as strong as a covalent bond. It's a weaker interaction. So it's about 20 kilojoules per mole. But that's enough to influence, the melting and boiling points of the material. We'll talk a little bit this semester about the importance of hydrogen bonding in amines, amino acids. So in proteins, which are just polymers of amino acids, a lot of the function comes from how hydrogen bonds happen in those molecules. So you have a sequence of amino acids that makes up a peptide, which is a protein, and that protein has a specific function in your body. And for example, if you're taking a prescription drug, that drug is interacting with a protein through hydrogen bonding interactions. They never really form covalent bonds. So it goes to the protein, it does its thing, and then you excrete it. So just keep in mind, sort of the spectrum of bond strengths. You have these non-covalent ones, which are really weak, covalent ones, and then what you learned in Gen Chem, ionic bonds, like sodium chloride, which are really strong. So before we get into actually making alcohols, we'll talk a little bit about the reactivity of the OH group itself. And the first slide is called basicity. So if the OH group is acting as a base, that means it's going to abstract a hydrogen. On the next slide, we'll see it can act as an acid, where it's giving up that hydrogen. So overall, it has this word amphiphilic reactivity. And generally speaking, it can act as a nucleophile or an electrophile. Something's happening with my slide here. Okay. So in the next two slides, it's either acting as a base or an acid. But again, more generally, we use the term nucleophile, electrophile. So if you take an alcohol, this is 2-butanol. We put in our lone pairs. If you react it with H3O plus, which is hydronium, so that's an acid, the alcohol has to act as a base, which means it's going to abstract a hydrogen. So we start at the lone pair. We point towards the hydrogen. We then break the HO bond, which loses water. And now look at the name of this. It's no longer called hydronium, it's called oxonium. And it has the plus charge because the oxygen's no longer in the neutral valence state. The thing to keep in mind, under acidic conditions, the more we learn about mechanisms, the reactive species has to be neutral or positive. So it says oxonium ions typically ionize to form carbocations. So what we've done is we've taken OH, we've activated it, and then that can further ionize to form another equivalent of water. And now the plus charge is on the carbon. So alcohols can also act as acids. That means the H of the OH group is going to react with a base and it's going to get abstracted. So under basic conditions, say we're treating with sodium hydride. So that's a base. The lone pair on hydrogen, I'm going to just draw this out like that. That lone pair will abstract that hydrogen and then break that HO bond. So we would lose hydrogen gas. And now this is called an alkoxide. So the nomenclature IUM means positive, IDE means negative. So under basic conditions, you're either forming something neutral or negative. So notice the negative charge on the oxygen now. So the oxygen ends up being now basic or nucleophilic. So the pKa of your typical alcohol was about 16. And so the last prompt here says, do you recall how base strength affects the equilibrium? So if the pKa values between your alcohol and the conjugate acid, so hydrogen here is your conjugate acid. If the pKa values are too close, you just get a back and forth equilibrium. But if they're big enough, you drive it all the way to the product side, which is typically what you want. So as we go through learning, mechanisms, we still have to recall that going from A to B in a mechanism, there's this energy diagram that we talked about, the reaction coordinate. And so that's typically on the x-axis is time, is one way to think about it. And on the y-axis is energy. So if you had something that looked like that, there's a couple points that we needed to remember. So if we're starting here, we'll say point A, and we're ending here at B. So A is what you're starting with, B is your product. It says, we'll call this C, D, and E. Where would the intermediate lie? What'd you say? So D is an intermediate. C and E are transition states. So those things we showed before, the oxonium ion or the alkoxide ion, those are intermediates. They're formed and then they go do something else in the reaction. Transition states are always the highest point. And then anywhere along the way there's a sort of well, that's an intermediate. So there's probably one question like that on the final where you're given some graph that looks like that and you're asked to point out what's a transition state, what's an intermediate. So referring back to the acidity, so if we take an alcohol, we treat it with a base, we're forming an alkoxide, and then the conjugate acid of that base. What's important is how we draw those arrows, whether the difference in the pKa between the two acids is large, we favor the products. If it's closer together, it sets up an equilibrium. So on the next slide, we'll look at phenol, that's the aromatic alcohol. Versus cyclohexanol. And so cyclohexanol, the pK is 16. For phenol, it's 10. So remember, the trend was lower pKa is more acidic. If each OH group is bonded to carbon, and they both have 6 carbons, why is phenol 10 to the 6 times more acidic? So phenol has something that the cyclohexanol does not. And as we work through the next slide, we'll see the reason why. Like what other factors in the molecule affect the acidity of the OH group? Like OH is OH. Like, shouldn't it all just be 16, So if you had the alkoxide of cyclohexanol, and then you added or titrated in phenol, it would do a proton transfer, because that difference is 10 to the 6. Remember, acidity is a log scale. So we draw the arrow just one way, meaning that it's going to go that way and it's not going to go the other way. So if this alkoxide acts as the base, it's going to abstract that hydrogen, put the negative charge on the phenol oxygen. And so what phenol has that the other one doesn't is that negative charge can be stabilized through resonance now. So through resonance, you can move that negative charge around the ring, and that's a stabilizing factor. So even though, again, both have OH, that other structural feature makes it more acidic with phenol. Any questions? So the last half of the lecture, we're going to talk about how we can take carbonyl-containing functional groups. So that's carbonyl is a CO double bond. How can we take reagents to reduce that down to the different alcohols? So the mechanisms for whatever reagent we're using are pretty much the same in terms of what happens of taking that carbonyl to the alcohol. In general, nucleophiles are sources of electrons. So like a lone pair, as we saw in Module 1, the pi bond of the aromatic ring, something that's supplying the electrons to form the bond. Electrophiles are an electron sink, so they're accepting. And all of this really gets back to, these theories of acids and bases. So the most general theory is the Lewis acid-base theory. And then within that, we say a Lewis base is a nucleophile. It's supplying electrons. A Lewis acid is an electrophile. It's accepting electrons. The arrow will always start from the nucleophile and point towards the electrophile. So this is your little quarterback, he's throwing the football to the receiver, and the receiver is catching it. So nucleophile, electrophile, that's the flow in terms of the curved arrow. One thing, and I'll try to do it regularly this semester, is always number your carbon skeleton so that on the final there's some cheap responses for some of these questions where the carbon count is just totally off or it's different. And so those are your distractor responses. But you want to number it so you know what's being formed and what has to break in terms of the bonds. Anytime you form a new bond, typically you have to break an existing bond. Acidic media are neutral or plus charge, and basic media are neutral or negative charged. So while the module exams, they're open 24 hours a day, you can use your notes, your book, whatever. You still want to develop an intuition so that when you're going into the final, you know what a reagent's going to do. Is it going to be a reductant? Is it going to be an oxidant? What functional groups does it act upon? So you still need, that general intuition. So we ended last semester by looking at how to make alcohols and ethers from alkenes. So alkenes are a carbon-carbon pi bond. What's new this semester is we're going to make them from carbonyls, which is a carbon-oxygen pi bond. So as you'll notice when our common starting material here, 1-propene, there's no oxygen in that starting material, right? So every reagent must then contain the oxygen that you're putting into the molecule. What we'll learn today is that the oxygen is already in there, and we're just going to add some other stuff to it. So the first one here, I think, was called hydration. That was using like hydronium. The second one was hydroboration. Oxidation. That used borane, THF, and then we had to do this sodium peroxide workup. This third one was called dihydroxylation. That was osmium tetroxide. We also learned how to make ethers, so specifically epoxides. That's the 3-membered ether that used MCPBA. And then halohydrins. So alcohols are also called hydrins. Again, there's a lot of names for things. And this was, say, bromine in water. That's when we were taking, the alkene and then adding electrophiles to the alkene. So to set the stage for this module, but the subsequent modules, I said at the beginning of today's lecture that this was oxidation state 1 functional groups, and then the rest of the modules are organized according to oxidation state. So oxidation state, or sometimes I'll write just OS, you're just looking at the carbon and seeing it as a heteroatom bonded to it. and that's anything other than carbon or hydrogen. So these are all heteroatoms. And then from that carbon, does it have 1, 2, or 3 bonds? If there's no bonds to a heteroatom, it's oxidation state 0, so it's like an alkane. So if we go down this table here, so we have oxidation state 0, that would be CH4 methane. If we substitute a hydrogen for an OH group, so the way to think about it, now that carbon is at oxidation state 1. You're just counting C to O, there's 1 bond. So this is oxidation state 1. The hybridization still stays sp3. Now what we're going to do in going up to oxidize that carbon, one way to think about it is look at the carbon, look at the oxygen. We're going to remove the elements of H2. So oxidation, a way of thinking about it, is removing hydrogen. So if we remove this H and that H and form a double bond between them, now there's 2 bonds. So 1, 2, this is oxidation state 2. And now the hybridization changed to sp2. We can further oxidize, where now we're substituting one of those groups for a heteroatom. There's a mistake here, that should be sp2 right here. So we've gone from alkane to alcohol to aldehyde. Now we're going up to the carboxylic acid oxidation state. So we have 1, 2, 3 bonds. The highest oxidation state you can get is 4. So that carbon is sp hybridized, so that's correct. And so that would be carbon dioxide. So everyone, I know I'm not the most engaging speaker, but take a deep breath. Exhale. You're exhaling carbon dioxide. And I have this scale at home. Do you ever weigh yourself in the morning? You're like a pound or 2 lighter. It's like, what's happening? Like obviously you pee, right? But the majority of like the weight that you lose overnight, you're just exhaling carbon dioxide. You can lose like 2 to 3 pounds every night just through normal metabolism. It's pretty fascinating that, you obviously wake up thirsty, right? I mean, because that's your metabolic processes breaking down like glucose and fats and things into CO2. So like you're exhaling a pound of like CO2 or more per night. It's pretty wild. If you're an athlete, I think it's like 3 to 5 pounds or something. But the oxidation state is important because as we classify it and then we learn the reagents are tied into those oxidation states. So some reagents only go for oxidation state 2, some only go for 3, some do 1 through 3, and that's how this is organized. So if you increase the number in oxidation state, so 0 to 1, that's an oxidation. 2 to 3, you can go 1 to 3. And so I call that a 2-stage. You're most likely going 1 to 2 and then 2 to 3. But overall, the change is going from 1 to 3. If you decrease, that's a reduction. So 3 to 2, 3 to 1, 1 to 0. And as you're most familiar with, these reagents, they'll typically have hydrogen in the reagent. So that's how you can sort of clue in that a reduction is going to happen. So now getting on to how do we actually make these? And again, we're going to use carbonyl-containing functional groups. So that's the CO double bond. We saw a lot of them in Organic 1. There's a lot of different carbonyl-containing functional groups, and we'll see them in a slide or two. The carbonyl group is a sigma bond, a pi bond, and then oxygen has its lone pairs. So the oxygen's delta minus, the carbon's delta plus. And just as a review, if we were to draw in a dipole moment where we actually show the vector, where there's the plus, we sort of draw this cross, and then we point towards the negative. The reason to do this sort of activity is because you see that carbon's delta plus. That means it's electrophilic, which is telling you that a nucleophile has to attack there. If the nucleophile is supplying the electrons, it doesn't want to go near that oxygen because the oxygen's already delta minus. So the carbonyl carbon is delta plus, it's electrophilic, it's attacked by nucleophiles. So as I said before, if something's attacking that carbon to form a new bond, you have to break an existing bond. And the bond that you're going to break is the weaker bond there, the pi bond between the C and the O. So in preparing alcohols, alcohols are at oxidation state 1. Carbonyls are oxidation state 2 or 3. Overall, it's a reduction. If you start at oxidation state 3, it can go down to 2 or it can go down to 1. So ultimately, if it ends up at 1, it's an alcohol. So let's just draw some structures so that we're clear on the functional group names and their oxidation states. So we have OS1, 2, and 3, and we're asked to say, okay, which one best classifies these functional groups? So OS1 has to be an alcohol. So that eliminates A and C. Just sort of abbreviate it like that. OS2 is just the carbonyl group. There can't be any other heteroatoms bonded to that carbon. So that would eliminate ester. And OS3, this is what your ester would look like. A carbonyl with another oxygen that's bonded to a carbon. So we would get B. So what I mean by all of this is, say we're starting with this ketone called propanone. And as a review, functional groups that end in ONE are ketones. And then the first part of the name is telling you the carbon count. So propane is 3. A 3-carbon ketone is propanone. That carbon is oxidation state 2. And then overall, when we look at the product of the reaction, that's 2-propanol, so that carbon's 1. So we went 2 to 1. And so now, what reagents will carry that transformation out? So again, my advice to you is, when you're learning these, do the oxidation thing first. See if the carbon's being oxidized or reduced. And then you can start, memorizing the reagents. So as I said, there's a lot of carbonyl containing functional groups. Here's the ones that you learned. Here's sort of the line between 2 and 3. So aldehydes and ketones, remember the aldehyde, the carbonyl is at the end, so you have that H. A ketone, R1 and R2, are both carbon. And then when we go up in oxidation state, the heteroatom is changing. So we have OH for the carboxylic acid, O carbon for the ester, chlorine for the acid chloride. The anhydride has 2 carbonyls. The amide has the nitrogen. And then, although it doesn't have a carbonyl, the nitrile is still at oxidation state 3 because it's a triple bond. So to prepare alcohols at oxidation state 1 from carbonyl groups, you can start with the oxidation state 3, then go down to 1. So if you count just on top of the arrow here, that's 1, 2. So I call that a 2-stage reduction. If you start at oxidation state 2, you can go down to 1. That's only occurring through 1 step, so it's a 1-stage reduction. So we'll learn 2 ways of doing this, specifically related to the reagents. The first set are called hydride. And so hydride is H-, which means there's some other metal associated with it. And then the other set of reagents are called organometallic. And they're just basically carbon anions, so carbon with a negative charge. There's 2 main hydride reagents for this class. There's many more, but just for organic 2, the 2 that you have to know are shown right here: sodium borohydride and lithium aluminum hydride. So remember I said that this reagent, borane, that was used in hydroboration oxidation. Notice it lacks an octet, right? So it has an empty p orbital. So if you add hydrogen to it, it now has an octet, but it's also carrying a negative charge. And so that's balanced out by sodium. And overall, it's making those hydrogens equivalent to H-. And lithium aluminum hydride's the same way. So that hydride in the name is telling you it's a reducing agent. The organometallic, organo just means carbon, metallic means there's some metal. These are carbon anions. So we'll learn how to make those. And then we'll look at the structure of the alcohol and see how we can sort of design a synthesis to make that alcohol. If you recall from Organic 1, how we made, we take alkanes and then we made alkyl halides. This was the radical substitution. We can then take those alkyl halides and make organometallics from them. The metals are typically +1, so lithium plus, sodium plus, potassium plus. Or you can use +2, such as magnesium. You can imagine that a carbon anion is very strong. This is where we'll spend some time talking about whether the anion acts as a base, which wants to grab a proton, or a nucleophile, which means it wants to attack carbon. So because of that issue, we need to talk about solvents and what solvents are appropriate to run these reactions in. The mechanism, whether you're using hydride, which is H-, or the carbon anion, is the same. And so I'm showing a carbonyl group here. And we're going to say that R1 is carbon no matter what. If R2 is H or carbon, that's an aldehyde or a ketone at oxidation state 2. But if it's R3, which is a heteroatom, then it's oxidation state 3. But regardless, say we have the nucleophile is H-. It's going to attack that carbon, which is delta plus. The oxygen's delta minus. And then we break that pi bond. So we're forming this new bond here. And then oxygen gets a negative charge. And the mechanism is called nucleophilic addition. The other thing to note is that the carbon hybridization changes from sp2 to sp3. So it's now tetrahedral. The reason the original oxidation state matters, because I said there was this 2-stage and 1-stage. If you start at oxidation state 2, basically when you add acid, so hydronium ion, all you're doing is protonating the negative charge. And you end up with your OH, your alcohol. If you start with oxidation state 3, where that group was a heteroatom, now it goes through another thing called elimination. These are typically good leaving groups. So rather than being protonated to form an alcohol at this point, a lone pair will come back down to reform a pi bond, and then that group gets eliminated. So you're ending up with an oxidation state 2 compound that will then undergo this process again. So one more time, it gets reduced down to the alcohol. So keep in mind, it'll undergo 2 additions. So sodium borohydride and lithium aluminum hydride react differently. Sodium borohydride is kind of weird. You actually run these in alcohols, but normally these reagents you wouldn't do that because they would just do acid-base chemistry. Lithium aluminum hydride is much more reactive, so you have to use an ether solvent. So there's diethyl ether, or THF, is a cyclic ether. And so the highlighted green means for that oxidation state, that reagent will work. If it's red, it will not work. So what you notice with sodium borohydride, it only works on aldehydes and ketones. And lithium aluminum hydride, I call it the hammer. If your only tool is a hammer, everything looks like a nail, it reacts with everything. It's just going to reduce that carbon down as much as it can. And so here's another table that will help you determine like what you're starting with and then what class of alcohol you end up with. So sodium borohydride or lithium aluminum hydride with an aldehyde will always give you a primary alcohol. Ketones will always give you secondary. And then with lithium aluminum hydride, as you see in green there, they're always giving you primary. Really the difference between them, the ketones, because that carbonyl is internal of the chain. So when you reduce it, you're adding an H, it has to end up secondary. Amides and nitriles are a special case, and we'll talk about those separate. So right now we're just talking about alcohols. They end up giving amines because they react just a little bit differently. So here you have a starting material that has 2 main functional groups. We're reacting it with sodium borohydride in methanol. How many labs have you guys had so far? Did you do anything or was just check-in? Okay. You might actually do a reduction in lab. These reductions are pretty fast. I mean, as soon as you add the sodium borohydride, you analyze it by TLC, it's essentially done. So you have this molecule, it has 2 functional groups with oxidation. So that's oxidation state 2. This is oxidation state 3. So an aldehyde and an ester. And so we recall from the prior slide that sodium borohydride only acts upon oxidation state 2. So it's got to take that carbon all the way down to oxidation state 1. It's not going to touch the ester, so the ester is going to remain intact. So H minus will add to that carbon. We break the pi bond, and then on workup we protonate. So that has to go down to oxidation state 1. So which product do you think looks the best for this? So B. This is staying at 3. This is now at 1. So we've gone from 2 to 1, that's the reduction. And then if we classify this alcohol, it's a primary alcohol. So a word that you'll see is chemoselectivity. And that means which functional group the reagent will act upon. And as you do your reading, you do problems, you're developing that intuition so that you're not at the point where you throw your hands up and say, I have no idea. The point of this stuff is that you're rationally able to predict what is going to happen. So that's the strategy. So same molecule, same oxidation states, but now we have lithium aluminum hydride. That acts on OS2 and OS3. And so what would be the product for this? So C. They're both going down to oxidation state 1. So maybe I'll throw out, maybe you're wondering this, maybe you're not. We saw sodium borohydride only reduced the aldehyde. Lithium aluminum hydride reduced both. But what if you want to reduce the ester and not the aldehyde? So what if you wanted to form A? How could you do that? Okay, you'd have to block it. So you have to take that aldehyde, make something else out of it, then reduce the ester, and then deblock the aldehyde. So that is something we'll learn, I think, in this module as part of reactions of carbonyls. And you know, as a preview to that, this carbon here, it's sp2 hybridized at oxidation state 2. In terms of the strategy of how you do this, there's a set of reagents that will take it to sp3 hybridized, but it keeps the oxidation state at 2. And so that's called a blocking technique. And because the oxidation state does not change, we just say those groups are functionally equivalent. So we're at about, we have 5 minutes. I hate to cheap out, but I don't want to start this and then like cut off. I just want to talk about it all at once. So those hydride reagents only introduce H. So the next thing we'll learn are these organometallics. And those are going to introduce carbon nucleophiles. And so that's going to allow us to make virtually any alcohol we want. And so to set the stage for that, we'll look at an alcohol and we'll sort of think backwards. What carbonyl group could it come from? Look at the product and then sort of guess what the starting material would be. And that's another strategy in this class of design with the reagents. So we'll stop there and then we'll start on Wednesday with the organometallics. Don't forget to do your quiz, and I'll talk a little bit more about the grading scale and stuff on Wednesday of how your letter grade is determined from your points.